As a cosmologist, I am privileged to be at the forefront of human exploration, looking at the mysteries of the entire universe. But I'm not only interested in such cosmic questions, I'm also interested in revealing what it takes to be a professional, to do things not like our friends Neil deGrasse Tyson, Carl Sagan, Richard Feynman, Albert Einstein, but as an experimentalist, because I get to play with the most exciting cutting edge equipment built by my collaborators and friends all around the world, and even sometimes shooting them into space.
That instrument can actually measure the mass of neutrinos.
And recently I shared this privileged position that I have with my friend Abhijit Chavda's audience on his incredible podcast. We talked about new and exciting breakthroughs that have been making headlines around the world.
Yes, there's been a couple of severe crises in cosmology. And crisis is not a bad word. Crisis kind of is what scientists live for.
But we also dove fearlessly into the most fundamental questions in cosmology and even in society. Protest, violence on campuses, and the future of academia.
Some scientists hate the multiverse. They actually think it's bad, not just for scientists, but for society.
So, without further ado, let's get this episode rolling. Thanks to Abhijit for having me on again. It's always a pleasure.
So, Dr. Brian Keating, it's almost 2 years since we last spoke. Welcome back to the podcast. How have you been?
I've been great, and it's such a treat and an honor to be back with you. I've followed your success, tried to model your success, and I'm a quarter of the way there. So, thank you for being a guide and a mentor, Abhijit.
I'm very pleased to see the growth of your podcast and your channel. It's really good to see a science communicator and a genuine scientist doing well, and people want to watch that. So congratulations. That's great to see, really.
Thank you so much.
So we're going to talk about a number of things. Let's begin with new discoveries and breakthroughs in cosmology. So what's new? What's exciting? What have you been following? And what have you been doing?
The most important thing, I think, in the last couple of weeks, has come from my fellow cosmologists that study the universe via the patterns that galaxies make when they cluster together in the early universe. And this pattern of galaxy clustering is called baryon acoustic oscillations. It's a big fancy word for meaning most of the matter in the universe is dark matter. We don't know much about it. But the matter that we can see, even though it makes up a tiny fraction of the universe's total amount of matter and energy, is the only matter we can see. So it pays to pay a lot of attention to that. And I always talk about the different types of fusion that occurred. We're familiar with nuclear fusion. That's very important. That made the very first elements in the periodic table, the hydrogen, helium, lithium, beryllium, etc. And then later on, there was the fusion of the first atoms when you had a hydrogen atom form from an individual proton and an individual electron. When that happened, you have a fusion event that produces a signal that we can see today. And then later on, you have the fusion of the first stars, and the stars start to come together and and form galaxies. And then those galaxies form clusters. And the thing is, their patterns trace out all the matter, all the energy, and the structure of space and time itself. And by doing that, we can actually measure the properties since that light was created all the way through to today. So that light was created maybe a billion years after the Big Bang occurred. And now we see it today. And all those photons have traveled through space and time. And along the way, they carry little messages. Those messages tell us about the state of space from their creation 12 billion years ago to today. And recently, it's called the Dark Energy Survey Instrument, DESI. It made an announcement that was really quite shocking because it really revealed two things. One, that the universe is expanding at an accelerating rate, and I can communicate what that means in just a bit. But it also revealed the properties of, there is one form of dark matter, Abhijit, that we know exists. It's called neutrinos. Neutrinos are elementary particles. They have mass. We know for sure they have mass. We don't know what that mass is. I'll get to that in a second. But neutrinos are associated with radioactive decay and other processes in the early universe, and they're incredibly important to the study of the structure of the universe. In particular, since they have mass and they don't interact with light, they are dark matter. And this team, the DESI team, made the first very strong constraint on the mass of these neutrinos. They make up 3 of the 17 elementary particles. You've heard of the Higgs boson, you've heard of quarks, you've heard of the electron. Well, the neutrinos are 3 out of 17, and we don't know what their masses are. They're the last missing pieces on the periodic table of the elementary particles. And so it's an astounding breakthrough to now have a limit, not coming from CERN, not coming from the Large Hadron Collider. For the first time in history, cosmologists, people that look through telescopes, are now setting limits on particles instead of those people that work in Large Hadron Colliders and things like that. So it's an astounding time. We don't know yet their mass. We think with my instrument that my colleagues and I have built over the last 8 years, called the Simons Observatory in Chile, where I just was a couple weeks ago, and I will talk about that, I hope. That instrument can actually measure the mass of neutrinos. In other words, right now we know if I looked at you and I said you weigh less than 100 kilograms, but you weigh more than 90 kilograms or something like that. I'm just making that up. I have no idea. We've never met in person, but I hope we will when you come to LA or I come to India. But the point is, Abhijit, we only have an upper limit and a lower limit, but we want to detect it. We want to know exactly what it is. We'll be able to do that in the next few years with instruments like our collaboration, Simons Observatory. So it's an incredible time. For the first time in history, astronomers are measuring particles. And it's there's no telling what will happen after that, because it's a philosophical shift as well. Will my colleagues that work at the Hadron Collider, will they trust me as an astronomer to measure what they do? I don't know if I would trust them if they said, well, I used the Large Hadron Collider and I measured, the sunspots. I don't know if I'd trust them, but we'll see what happens. It's a revolutionary paradigm shift for science and philosophy.
So what is the Simons Observatory and what does it do and how are you measuring the neutrino masses?
So it's a fascinating observatory. It's built by funded by hedge fund billionaire Jim Simons, who is an incredible philanthropist. He and his foundation and his wife, Marilyn Simons, and our partner institutions have come together and funded it for construction. It's built in Chile. It's in the northern part of the Atacama Desert of Chile, near the Andes Mountains. It's near an active volcano. It's at 5,200 meter elevation, so 17,000 feet above sea level. So when I'm up there, I have to wear oxygen and you have to wear helmets and you have to wear protection. It's freezing up there all the time, even in the middle of summer. And this instrument consists of 4 telescopes. Those 4 telescopes have a mission to measure the fluctuations in the cosmic microwave background radiation, or CMB. This is the 3 Kelvin heat left over from the production of the first atoms, not the elements, the first atoms when hydrogen formed about 500,000 years after the Big Bang. When hydrogen forms, just like any fusion, like when you fuse together 2 protons and neutrons, some excess heat is left over. And that heat that's left over, we see it today as the cosmic microwave background. It comes in all directions. You can't tune it out. And it's as if we're inside of this oven. And the oven is slowly trying to heat us up, but it only has the power to heat us up to minus 270 degrees Celsius. So it really doesn't work that well as an oven, but that's good, because if it was really hot, we wouldn't be here having this conversation. So the CMB is the oldest light in the universe. Oldest, it was visible at one point, but now it's in the form of microwaves, just like an oven. We can't see microwaves in an oven, but we can detect their presence by what they do to other forms of matter. As these photons, these particles of light, travel from the early universe to our telescopes today, the Simons Observatory makes a measurement of their distribution on the sky, and in particular looks at their polarization. What plane are the photons oscillating in? That's called the polarization. Imagine you and I are across a table, we're holding a rope and we're cycling the rope up and down. That would make a wave that would have a polarization plane like this. We could shift it like this and it would go this way. And the same thing happens if you have sunglasses that are polarized and you tilt your head when you look at the ocean on a sunny day, it will cause the intensity to modulate, to shift. And that's indicative of the interaction, not just the light itself, but how does it interact with matter? And in our case, we're trying to see something that was produced even before these photons were produced. And they're called waves of gravity, gravitational waves. So just like India participates in the LIGO Virgo project and has their own instruments, those are trying to measure gravitational waves produced by nearby structures, nearby being 1 billion light years away. We're trying to measure things 40 billion light years away when the universe was an infant. And in that time, and since that time, they have been tracing all the matter, all the energy, everything that they've interacted with from that time till today. So it's even more pristine than the fluctuations that the DESI collaboration used to measure these neutrino or constrain these neutrino masses. So it's even older than that. And because human beings are naturally drawn to what they can see, not to what they can't see, we have the opportunity to use the oldest light to kind of trace fossils of when the universe was first born in the Big Bang. So last time we talked, you and I talked about Jayant Narlikar, who was a stunning cosmologist, still is, but he was an opponent of the Big Bang, and he still is. And we spoke at great length on my podcast, and I think you had him on too, right? Or you spoke with him?
I
Oh, you
did
didn't
not.
get to.
Not this
Okay.
far.
Yeah, so hopefully we'll make that happen. But he is a true amazing individual. And what he did is he started to make the first predictions of what you would see if the Big Bang truly occurred back in the 1960s. And his research came to the conclusion that the Big Bang didn't happen. And some of the evidence against his research comes from our field, the cosmic microwave background radiation. So what we're doing has the potential to kind of once and for all settle the question of, was there a Big Bang? Because if there's a Big Bang, there should be a fusion left over, not from the first galaxies, not from the first stars, not from the first atoms, not from the first elements, but from the fusion of space-time, the combination of space and time into existence about a trillionth of a trillionth of a trillionth of a second after the Big Bang. And so that's what we're trying to do at the Simons Observatory. Massive telescopes, and they're located at this incredible pristine location because we have to avoid, by any means necessary, contamination from, say, the atmosphere or other sources that can completely overwhelm what we're looking for.
Hey there, sorry to interrupt the podcast, but I've noticed that even though you're enjoying this podcast, no matter where you are in India and America and Canada, about half of you aren't following or subscribing to the podcast. So while you're here, why don't you subscribe to the YouTube channel and follow me on your favorite podcast app of choice? While you're there, leave a review or comment or a thumbs up. It really does me a favor with these algorithms that really do influence what gets seen and how the message gets transmitted throughout the cosmos. So do me that favor, won't you? Okay, thanks. Back to the episode.
And what else is happening right now? In the past couple of years, have there been any new breakthroughs in cosmology?
Yes, there's been a couple of severe crises in cosmology. And crisis is not a bad word. Crisis is horrible in politics and peace and all sorts of other things. I hate crises, on a daily basis. But crisis kind of is what scientists live for. Because if you have a theory and it's completely understood and it makes all these predictions, then effectively you're kind of like a stamp collector, or you're doing important work, but it's not novel. It's not doing something that's never been done before. However, when you see something that doesn't fit into the prevailing wisdom, the scientific paradigm, the philosophy of the time, it's incredibly exciting. It's exhilarating to scientists, professors like me, because it means that we don't understand something. And so what we love to do is hunt for new explanations, new paradigms that people could not find before because the technology wasn't there. So an example, in the 1700s, Isaac Newton came up with his famous theory of universal gravitation, and that predicted the inverse square law. And he had to invent calculus, and he did incredible things, incredible works. What was almost as important as what it could predict, namely that planets should move in elliptical orbits with the sun at the focus, etc., was that it had glaring gaps, flaws, lacunae, things it could not explain. And that led a young man in the early 1900s by the name of Albert Einstein. I have puppets of everybody here. Here's Albert Einstein. Albert Einstein to say, wait a second, there's something weird with your theory. It does predict things exquisitely accurately. And for example, it is able to solve a problem which it shouldn't be possible to solve. You've heard of the three-body problem. It's a famous book,
Yes.
but it's also based on a physics problem, which is that if you have three masses, so here I've got a one chunk of meteorite, which I give away. I'll have to ship it to people in India, but one lucky winner a month wins one of these. Here's another meteorite, and then let's say they're circling around me, but they're also interacting with each other. In general, the orbit is unpredictable. You cannot predict the orbits of just simple planets if there's more than two. That's a general principle. That's called the three-body problem, and what arises from it is called chaos. You have chaotic behavior, where the behavior, if you start the planet off at one location, you change it by a millimeter, eventually you get completely different orbits that we can't understand. But Einstein realized, wait a second, besides that, In certain simpler situations, say just the planet Mercury orbiting around the sun, ignore the Earth and ignore all the other planets, but just look at Mercury. It doesn't do what Newton predicts. And in fact, it's moving in an orbit. It's an ellipse. And every time it gets closest to the sun, it's shifting a little bit every day, every year. That elliptical orbit is precessing, and nobody could understand it. And Einstein said, wait a second, what if gravity not only affects space, it not only causes space to kind of curve and warp and bend the trajectory of light, but it also shifts time. You see, Newton thought time was absolute, that time ran at a fixed schedule, no matter you here, me here, you in India, wherever. You and I had a coordinated clock that would always agree on every event. Einstein's theory of special relativity said that's impossible. You cannot have two observers in different locations in space, moving at different velocities, have the same coordinated time. It's impossible. But they will agree on one fact, only one fact, that the speed of light is the same for you in India in your laboratory as it is for me in San Diego, California in my laboratory. That's the only thing they'll agree upon. And he constructed the mathematical framework by which you could have a set of observers, and what they would agree upon is only the speed of light. And in doing so, you had to sacrifice the absolute nature of time. The only way that could happen is if time and space were pliable, that they changed, that they were not fixed quantities. And that was his theory of special relativity. And then in 1914, he started to think, well, wait a second. If that's true, then we can't explain how Mercury is behaving. It's behaving in this weird orbit. The only way we could actually affect that is if gravity also affects space and time. And when you do that, you find you not only can't constrain how clocks move in your laboratory, but you cannot in general do it throughout the entire universe. And so by doing this magical kind of mathematical manipulation, Einstein was able to derive and retrodict. If I say tomorrow, Modi's going to do something, whatever, that's a prediction, right? But if I say, now I understand why he did this in the past, that's a retrodiction. Now it's easier with people in some ways, harder in other ways. But with planets in the solar, it was easy to understand, to collect this data and then apply it in reverse. And that would have been a tremendous accomplishment. That would have been one of the greatest accomplishments in the human mind. But Einstein then said, well, let me make predictions. You should see the following thing happen. During a total solar eclipse, as we just had here in America, we had a perfect total solar eclipse on April 8th. And when that happens, the sun is being eclipsed by the moon. When the moon passes in front of the sun, that allows you to see stars you can't see normally, like the light behind me. If I move it, if I'm the moon now, I block it out. There could be stuff behind me that you can't see because the glare is too bright. Einstein predicted that the stars behind the sun should bend by a tiny amount if the theory was true. And later it was proven that he was correct through experimental observations. So that was a tremendous accomplishment that no one had ever done before. And rightfully ended up getting him the notoriety, and he won the Nobel Prize 2 years later. So this has had a long kind of impact on culture, on philosophy. And the same thing is happening with our telescopes like the Simons Observatory. We're really trying to revolutionize how does gravity affect the origin of space and how does it expand? So you asked me, what are the big crises in cosmology right now? One of which is that the universe is expanding, according to some, faster than it should be. And the speed of the expansion is inversely related to the age of the universe. That is, if I say you're moving away from me at 1,000 miles an hour, but you're only really moving away at 500 miles an hour, to get to some greater distance, that means you had to be expanding longer, right? You had to be traveling for a longer period of time at a slower rate to reach the distance that we see now. That's what's happening in cosmology. We have two different teams. They disagree violently. Each one says, I know my answer exactly, precisely to about 1% accuracy. And the other one says, I know the same thing, but they disagree. They argue about the age of the universe. It could be 14 billion years on the oldest side, and it could be 12 billion years at the younger side. That's a huge uncertainty, especially when both are saying, I know this as a fact. So that's called the Hubble tension or the Hubble crisis. That's one of the biggest problems in cosmology, aside from the fact that we don't know anything about dark matter and we don't know anything about dark energy just yet. And so these are huge things. And yet, it's not like we don't know anything. We know the age of the universe to the equivalent of looking at you and saying, I know what day you were born, basically. So it's an incredible time to be a cosmologist. The more crises, the better. Bring them on, as long as they're not political.
There was this recent survey called Pantheon Plus that was able to determine the Hubble constant to a very good accuracy. But the measurements of the CMB disagree significantly. So it's either 73 megaparsecs, kilometers per second per megaparsec, or 68. And that's a big problem. I mean, what do you think is the cause of this?
Yeah, so there's really only a couple of explanations. One is that the universe is fundamentally different. Let me explain how they're getting these different results. So there's two ways to measure the Hubble constant. The Pantheon, like you said, led by my friend and many-time guest on my podcast, Adam Rees, who won the Nobel Prize in 2011, along with other guests, Brian Schmidt. And the what they're trying to do is look at the universe today and look at how fast things are moving apart. They're spreading apart at some rate, and they spread apart faster the farther away you are from them. That's called the Hubble constant. You take the distance something is from you. If you can measure that, that's the hard thing to do. It's very difficult to measure distances. Just think of you looking at the night sky, the dome of the sky. You can't tell if a star is bright because it's close to you, or if it's intrinsically bright and it's far away. So there's no depth perception in astronomy. So astronomers have to make up proxies that trace what those distances are based on other measurements called the cosmic distance ladder. So they use the cosmic distance ladder. They get a measurement of the velocity of things right now, or right now being 1 billion years ago, 2 billion years ago, which is small compared to the age of the universe that my colleagues study, the cosmic microwave background. That's predicting how fast the universe should be expanding based on when it was young, assuming that we understand the physics that prevailed in the early universe, which is easier to understand because all there was hydrogen. The universe today is full of planets, asteroids, meteorites, dark energy, dark matter. Back then, none of that stuff really mattered. And so it's a cleaner measurement to use the CMB, the cosmic microwave background. It's more pristine. It doesn't have contamination as much, but it's as if I'm looking at my child when they're a baby and saying at age 16 or whatever, you're going to be growing 1 millimeter a month or something like that, versus measuring them right now and saying they're actually moving away 1 millimeter a month. If you like, their height is changing 1 millimeter a month, but they disagree. One says it's 1 millimeter and one says it's 1.2 millimeters. And that might not sound like much, but again, it translates to a billion-year error. If one of them is right and the other one's wrong, they're off by 1 billion years in the age of the universe. And yet each one has very mature techniques. I mean, the Pantheon survey is similar type of tool and approach that won the Nobel Prize in 2011. The CMB, the cosmic microwave background, is the same as won the Nobel Prize in 2006. So who do you trust? If you just say, I'm going to only listen to Nobel Prize winners, you don't know who to trust because they disagree. And they're using different techniques. Each one has strengths and weaknesses, but this is what makes it so interesting. So one could be wrong. One could actually have made an error. One of the two teams, they both could be wrong. I mean, we have to be open to that. Even though they have Nobel Prizes, who cares? We don't look to authorities. They're not gods. They're not deities. We always have to verify, confirm. And so they could both be wrong. One could be wrong. The other could be right. And then the other thing that could happen is that the universe physically could have changed. There could be some new component, some new attribute of the universe that we don't understand, that was in operation early in the universe's history. Remember, it's only 500,000 years old approximately when my colleagues used the CMB. And there could be some type of energy that no longer exists that caused the universe to expand more slowly back then, that you would predict it would expand more slowly today. Or there could be some contamination or something today that precludes us from understanding how far away these objects are now, causing my colleagues in optical astronomy to make mistakes. I think the more exciting, kind of attribute is, or possible explanation is that we don't understand what the universe was like in the earliest moments, and that could certainly have happened. It's happened many times in human history that we're led to a conclusion we cannot evade based on the physics, the astronomy, the science that we know today, but ends up later being accepted as part of the canon of scientific literature. And just as an example of that, if you go to Wikipedia, not the world's most famous, best source for science or politics or whatever, look you up on there, but you go there and you look up science. You just type in science. I mean, for most things about facts, when was the War of 1812? And, they get Wikipedia is right. Other things, you ask them about people, it's very biased. But if you ask, what is science? the picture that comes up, the emblem of all of science, from biology, DNA, chemistry, even branches of other types of science, from mathematical sciences, applied physics. You get an image of the cosmos. You get a picture of the Big Bang Theory. That is the paradigmatic example of what science is, at least according to however many thousand Wikipedia editors there are. So the stakes are very high in cosmology. We are kind of the oldest science, literally and figuratively. Since the dawn of humanity, people have looked up, come out of caves and looked up and said, where did this dome come from? How did I get here? And it's the only question that we might not be able to answer, because we're kind of trapped inside of this, 3-pound supercomputer, and we can't get out of it on our heads. We can't get out of it to observe from outside of it. Unlike my colleagues in biology, if they want to study frogs and how, if you mutate the 16th genome, gene on a frog, I don't know anything about frogs or biology, to be honest with you, but if you mutate them, it will have, it'll be able to bench press, 400 pounds. I don't know. I'm making it up. But you can keep doing that to many different frogs, and you can enhance some of them and you can not enhance others, and you have a control. In astronomy, I can't go to the sun and change its temperature and then say, well, how does that affect the sunspot pattern? Or how does that affect, the life on Earth? I can't do it in an experiment. But in astronomy, we have examples of literally 100 billion stars in our own galaxy, another 100 billion galaxies, each with 100 billion stars. So we can do statistical ensembles. We can say for every yellow star that we see, like the sun, we measure its temperature, and it's about the same as the sun's temperature. Every green star, every red star, etc. And they all have these, so we can make statistical ensembles. But, Abhijit, how do you do that when you have a single cosmos, as some of my colleagues believe, but not all, because many of them believe we inhabit what's called the multiverse.
You were talking about crises in cosmology. I mean, one of the instruments that's thrown up a lot of new information is the James Webb Space Telescope. And it's brought up some really interesting results. Like, the first galaxies, massive galaxies, are about 300 to 700 million years old. I mean, when the universe was about 300 to 700 million years old. So that kind of appends our understanding of what galaxy evolution should be like. And there's also theory that those could actually be dark stars that are annihilating dark matter. So what are your views on that?
Yeah, so that's very interesting. So the woman who popularized that is a good friend of mine and a collaborator on the Simons Observatory. Her name is Katie Fries, and I did an interview with her in my office, in my studio here in San Diego 5 months ago. She originated this idea of dark stars. So let me first say that James Webb Space Telescope, it's a phenomenal instrument. It has a diameter of about 6 meters. It's one of the largest telescopes ever launched in space, so big that to fit it into the rocket, they had to fold the mirrors on top of each other. And then when they got out, it kind of unfurled and assembled itself like origami in space. It's about 1 million miles away from the Earth in what's called the L2 Lagrange point that circles the Earth-Moon system. And it's been there since Christmas Day, December 25th, 2021. And this instrument is primarily designed to look for objects like the very first stars, the very first galaxies, the properties of exoplanets, their atmospheres. As a star has an eclipse. Imagine an eclipse of a star, or really a transit. When the moon or the planet that goes in front of the star is far smaller than the star itself, and even from its optical perspective, I mean, the moon is much smaller, but apparent size is exactly the same as the sun. On other planets, this doesn't happen. Like Venus can never make a total eclipse of the sun on the Earth, but it makes what's called a transit. And during the transit, the sun is illuminating not only the planet, which makes a tiny shadow, but it illuminates its atmosphere. And when light interacts with an atmosphere, it causes a characteristic spectral fingerprint that's completely indicative of what elements, what molecules are in the atmosphere of that planet. So when Venus does this, we see carbon dioxide, pretty much that's all we see. But some planets are starting to show other features, not only carbon dioxide, but they're also showing oxygen and other compounds. They could even show amino acids, which are the precursors to build DNA. So these are exciting discoveries that are taking place right now with the James Webb Space Telescope. And it may be that we get indirect evidence for oxygen and other, fingerprints of life. That doesn't prove that they're, podcasts on other planets just yet, but it would be sort of a crucial first step in discovering alien existence. Now, what the dark star hypothesis is that there are stars made primarily of dark matter, and that shouldn't really happen. An ordinary star formed primarily from the collapse of hydrogen. So hydrogen atoms form about 500,000 years after the Big Bang. When they form, it's the combination or fusion of an electron with a proton that produced the CMB radiation that I study. But it also provided the raw materials to make the very first stars. Stars are big nuclear fusion reactors that take isotopes of helium of hydrogen called deuterium, which has a neutron and a proton. Combine them together, 2 neutrons, 2 protons. That's helium. Helium is named after the god of the sun. In fact, it was discovered on the sun, not by going there at night, as I always joke to my kids, but instead by looking at the chemical spectrum and seeing the imprint of these new elements that had never been discovered on Earth. So the same thing can happen in stars in the rest of the universe, this collapse. But what Katie Fries and her collaborators are saying is actually it's occurring from the confluence of dark matter, and that produces this kind of nucleation point or fusion point where the star can actually emit light, but it's very low temperature. It's huge. These stars are enormous, 50 or 100 times bigger than our sun, much, much colder than our sun. And for those reasons, these are kind of an interesting candidate for both the first stars that would form, or how we could actually know how all structures in the universe are found. So she claims in an article that she she found the idea of these earliest stars that ever exist that are powered by dark matter heating up rather than nuclear fusion. And they actually make them out of, incredibly, they make them this at the center of these early galaxies, which would explain eventually why we have this huge black hole at the center of our galaxy, because they become, millions of times more massive than our sun. So I should say, it's just a conjecture right now. We have to get a lot more data from it, but the James Webb Telescope is really kind of custom made to find this almost ideally.
Do we know what temperature those stars have? I'm expecting they would be emitting infrared, right? Light?
Yeah, so right now they would be their light would have been stretched to the infrared, but in the earliest times they would have been created when they were produced. They would be much hotter, and they would be emitting at much higher temperatures, much higher, and that would cause their spectrum to be perhaps even out of the ultraviolet. So what Webb sees now is really only infrared radiation. So that's how they detect it. So today it's detected, but remember, if they're the earliest stars ever, if they're made in at great distances, this is corresponding to a redshift of about 10, which means the universe has increased by a factor of 10 since these objects produce the light that we're just seeing now. So the universe was 10 times smaller, and the wavelength of light has been stretched out 10 times. That means it was 10 times smaller in the reference frame at which the star produced the light. So it's an incredible, conjecture. They would have been incredibly massive, but they would have been cool at the time, like sort of tens of thousands of degrees Kelvin rather than millions of degrees Kelvin. And so this makes them visible today, but they require an enormous amount of dark matter for that to occur. And then eventually they could become these supermassive black holes, like the million solar mass black hole at the center of the Milky Way galaxy.
So is the heat produced by the squeezing together of the dark matter particles, or is there annihilation involved in this?
Yeah, so it's more related to annihilation. It's slow because
Okay.
a dark matter can't heat up. Heat really is the random vibration or molecular motion of ordinary molecules. So dark matter doesn't interact like that. It can accrete ordinary matter, and then that can heat up. So it's sort of a necessary condition, but it's not a sufficient condition. And so, yes, they can be annihilation, where dark matter actually is self-interacting, and that produces an ignition or an ignition source that can cause this star to start to glow, essentially, and cause the radiation to be emitted. But if you only knew about ordinary matter, you would think there's nothing emitting photons, which would be quite astounding. So that's what's so really delightful about this conjecture, is how they are producing this radiation without visible matter necessarily being the culprit for its production.
And recently, the Event Horizon Telescope has been in the news. It's captured a new view of the Sagittarius A star black hole at the center of the Milky Way, and it's discovered that it's got these twisted magnetic fields. So, what does this tell us about the black hole at the center of our galaxy?
Yeah, so I've talked to the founding director Shepard Dolman at Harvard about this many times on the channel as well. And what they're using is the same tool that my colleagues and I are using with the Simons Observatory, and that's called polarization. So remember I said the polarization is the plane of
Yes.
oscillation of a rope or something like that. In this case, the plane of oscillation of the electromagnetic fields. So you have brightness and then you have the polarization. Polarization is incredibly important because it tells you about the exact mechanism that the light is being produced under. Rather than just knowing the light was produced, it tells you how it was produced. In this case, when it was produced, this light was produced at the black hole. You might be thinking, first of all, how can a black hole emit anything? And this is very different from, say, Hawking radiation. Hawking radiation has never been observed. It's incredibly difficult to observe, but it seems to be a consequence of the combination of relativity and quantum mechanics. Leaving that out, this light that you're seeing in the patterns is caused by the heating of ordinary matter, of stars getting gobbled up by the black hole inside the event horizon. And then you don't see light at the very center, the shadow, so to speak, is where the black hole is. That even a star being gobbled up by the black hole, it will not have the light escape to reach our telescope. And by the way, this is radio telescope. These are much longer frequencies, longer wavelengths, and lower frequencies than what we see with even the Simons Observatory. So these patterns are indicative of the conditions where the black hole is in space and what happens to the matter right before it falls into it. And it turns out a black hole can really only have three properties. It can have a mass, it can have charge, and it can have spin. It can be rotating, angular momentum, it can have charge, and it can have a mass, as we know. And when you have a charge that's rotating, it produces a magnetic field. So these patterns that the Event Horizon Telescope is revealing using polarized light tells us about the motion of objects right before it goes into the black hole. And that, scientists think, is correlated to the actual properties of the black hole itself. Just like all the planets in our solar system, Abhijit, they all orbit in the same plane, more or less, and they all go in the same direction. That's a consequence of the formation of the sun from a collapse of a gas cloud and the conservation of angular momentum. Just like you see an ice skater and she has her arms out, she brings them in. When she's spinning, she goes faster. Well, we still retain the properties of the Earth's, of the solar system's formation, its rotation. And it could have been going either way, but it can't be perfectly symmetric or else we wouldn't be here because all the planets would have fallen into the sun. So the rotation keeps the planets from falling in, counteracts the gravitational force, centrifugal force. And so the same thing could happen with the event horizon that we're seeing here. The properties of the magnetic field that's revealed by polarization, those lines of force, they are tracers of the angular momentum of the black hole itself, potentially. So that we could learn about something that's completely invisible to us. We could see everything. The properties of this thing that we can't see with our eyes. It's a remarkable thing for scientists to witness. Again, all these things are happening at this accelerating pace. It's really overwhelming, even to me as a scientist.
Indeed. So this the magnetic field that we've discovered around our own black hole, it's kind of similar to the one that's around the Messier 87 supermassive black hole, which is about more than 50 million light years away. But that black hole has relativistic jets. Why doesn't our black hole have that?
That's a very good question. So our black hole is a lightweight compared to that black hole. Our black hole is, many, many hundreds or thousands of times less massive than that one. Now, the question is, how do these black holes get to be such behemoths? How do they get to be so large at distances farther away from us? 50 megaparsecs sounds like a lot. It's 150 million light years away. So that's a large amount of distance. The closest major galaxy to us is only about 3 million light years away. So this one's 50 times farther away. And yet it has this property. So it's not that much older than our galaxy. So it couldn't be that, oh, it's just older. It somehow either was born with more mass in that sense, and it had a region of space-time which had more hydrogen and helium that could eventually collapse, or dark matter, according to dark stars. And that caused it to collapse. Or there could be what are called primordial black holes, a black hole present at the beginning of time, even before the light that I study. So that could come about in a variety of different ways. One such way could happen is if our universe wasn't the first Big Bang. In other words, if there was a previous universe, and actually Giant Narlikar and his colleagues sort of suspected that our universe was kind of oscillating. It was a single universe, but it was there forever, and it would get bigger and smaller with time. And one of the modern day interpretations of this is made by my friend and many time guest on the podcast, Sir Roger Penrose, winner of the 2020 Nobel Prize. And he conjectures that the universe undergoes cycles of collapse and expansion, or, if you like, extreme expansion and then dilution. And then the dilution creates a new expansion, and that goes on forever. Other colleagues have suggested the universe collapses, comes to a point, and then re-expands again. Others say, no, it doesn't have to come to a point. It can go to a finite volume and then expand again. So this is this is another crisis in cosmology. We don't know what happened at time equals zero. I said we can go back 500,000 years. We can go back 1 second. We can go back a billionth of a second. We can replicate that condition on Earth very easily up until about a billionth of a second. But before that, we don't know. Trillionth of a second, we can't access right now. We may be able to do that with the cosmic microwave background type polarization that the Simons Observatory is now studying. But we don't know if the universe began, as Roger Penrose suggests, from another universe's demise, that there's only one thing that can survive the dilution, that never dilutes, no matter how much the universe expands, and those are black holes. And he calls these features called Hawking points on the microwave background. He claims to have seen them. I've argued that what he's seeing is not them, and others have as well. But it's an exciting field because there is one glaring omission, which is a feature of Sir Roger's theory, and that's that there's no multiverse. And you may say, well, that's weird. What's wrong with the multiverse? But some scientists hate the multiverse. They actually think it's bad, not just for scientists, but for society, because it allows for the possibility of literally anything happening. For you being born in San Diego, me being born in there, anything can happen, just like in the movies. Everything, everywhere, all at once. All the Spider-Man, all these movies try to depict what a multiverse is like. And some people call it unnatural, bizarre, anti-scientific. And so there are a lot of eminent scientists. We're talking the Einstein professor of physics at Princeton, my friend Paul Steinhardt, who believes that it's bad for physics and science and society to have a multiverse because there's no prediction. You can just say, well, the multiverse did it. Kind of like having a deity do it. Imagine if you had one God and every single event, you had the thunder god, you had lightning, you had this, you had that, and they're all different. That would be very bad. And it's almost like there's a pagan kind of propensity that people want to believe in this, kind of supernatural creation story. I try to be agnostic about that, Abhijit, as an experimentalist. I build a telescope. The data come from it. We analyze them dispassionately. I don't care who's right. I don't care if there was a Big Bang, if there was an infinite number of Big Bangs, if there's a multiverse, if there's a single universe. But instead, it's for the first time we can answer these philosophical questions using data. No one's ever been able to address these things. We can address them purely scientifically for the first time in human history.
It's me again with something very special. Do you want to learn about the most cutting edge topics in science, math, engineering, and culture? Do you want to join our cosmic quest and explore the multiverse of minds that I bring together on the Into the Impossible podcast? Well, you can do so in depth when you join my Monday Magic mailing list, where I send out 5 incredible magical aspects of our universe, ranging from cutting-edge scientific discoveries to the most fascinating discoveries by Nobel laureates, astronauts, billionaires, and more. So go to briankeating.com/list and you'll be entered to win one of these, a real piece of space schmutz, a meteorite, 4.3 billion year old fragment of the early solar system. So join us, won't you? And if you have a .edu email address, you're guaranteed to win. Go to briankeating.com/list. Now back to the episode.
What are your views on the multiverse? Do you think it's bad for society and for science?
I don't think of it as in quite those stark terms that my friend Paul does. I don't think that having a scientific idea is necessarily dangerous. I think there are ways to cause science. In America right now, politically, there's this huge divide where people are talking about just having no trust in authorities because of the pandemic. I won't say the word because I know YouTube listens to the actual words because they'll slap a warning on my channel, even if I'm talking about it in a positive sense. Like I had
Yeah.
Dr. Eric Topol, who is one of the foremost, kind of people that were terrified and tried to take precautions. I had people that Jayant Bhattacharya at Stanford. I had him on. He was the opposite. And even if I'm talking about it purely scientifically, YouTube will warn us. So let's not mention the word, but we all know what it rhymes with. So we have people now saying because of that, what happened in America with lockdowns and shutdowns and authoritarian science and certain doctors and so forth, and political candidates, that they don't trust anything. We had this guy, Tucker Carlson. You probably heard of him. He's almost as famous as you are. And he had this conversation with Joe Rogan, who I met on his podcast last year myself. It was a lot of fun. But when I was talking to Joe, I was very scientific. I didn't talk about politics necessarily. And this guy, Tucker Carlson, that's all he talked about. And in fact, he ends up saying things like, I don't believe in evolution. It's just a theory. I don't know how we got the fission bomb in the Manhattan Project. That could have been aliens. He said, I'm open to the idea of a flat Earth. He said that because I don't trust experts anymore. And it's to me, it's truly ludicrous that we've gotten to a point that's almost medieval again, and that sophisticated people are claiming these things, not unintelligent, smart people are claiming these things to advance an agenda of fear and reprisals against people they don't agree with. And that to me is much more dangerous than believing in a multiverse, because if scientists, and maybe we're responsible for it, I'm not saying scientists don't, manipulate their findings, that they don't become politicized. I think we do sometimes. Less so in cosmology and astronomy, because there's no votes you can get. If I believe in the Big Bang and you don't, I'm not going to get some extra, attention at the ballot box. But in public health, in energy policy, in climate change, et cetera, we should be very careful about using our scientific credibility that we earn in the laboratory and spending that in the political realm to advocate for policies or funding or control by the government. I think that's very dangerous.
Let's move aside from physics for a bit. You are Jewish. You were recently in Israel, September last year. And then 1 month later, the Gaza attack happened. The Hamas attack on Israel happened, the terrorist attack. How do you see, has the world changed a lot since then? And how has it been for you?
Yeah, I think it's been pretty horrific for me, for my Jewish students on campus. UCSD has had a great many demonstrations, including a day after the October 7th attack, October 8th. Palestinian student group, assembled a rally on behalf of the martyrs. They called them martyrs. And this is very common. Many of these groups have done this on college campuses right now. In late April of 2024, we're having huge encampments, protest, police being called in, violent rhetoric is being used. One of my friends is a dean at NYU, and they just had to call in the New York police to evict these people squatting, yelling just tremendous epithets and hurtful language. I'm all for free speech. I mean, it's our First Amendment in America, is the cornerstone to every other amendment. Freedom of speech, I think, is a human right. I don't think it should be limited to just America. but the point being, I'm fine if you say things, but you don't have the inalienable right to threaten people and to use hateful rhetoric. And I know if I were here and I was saying, things like Indians don't have a right to their country, or Pakistanis. Pakistan is illegitimate. It should never have been founded the same year as Israel, and it's illegitimate. It shouldn't exist. I would not have access to the campus later that afternoon. But Israel, it's okay to say Israel should not exist, to have pictures where Israel is erased from the map and declared to be Palestine. It's very troubling to me, Abhijit, because one of the fundamental aspects of being an academic, of being a professor, is academic freedom, that you have the right to study and associate, to be scholarly, And that includes doing things I don't agree with. If they can study Israel, we have a lot of professors, many Jewish professors do that. I'm not going to impede them, but the converse kind of not lack of hostility, or the converse acceptance of Jewish and Israeli scholars is not extended by my colleagues and friends, across campus, who don't believe that Israel should have the right to exist, let alone to have me be able to have my colleagues from Israel come to America. They want these colleagues to be boycotted, to have no ability to set foot on campus merely because they're Israelis. And I should say 90% of all Jews on earth are Zionistic, which means, they believe that Israel is the cornerstone of the Jewish people. It's mentioned in the Bible. Even Islam, the Quran mentions it 70 or 80 times. It's obviously a holy place, or else the Muslims wouldn't have their second or third holiest site, they call Al-Quds, which is the Temple Mount in Israel, where I was on September 7th. They wouldn't have it there, right? So obviously Israel's important. And to say that Jews have no stake in that, they have no right to be in Israel, is almost like ethnic cleansing. Like, they don't want my fellow Jews to live in Israel, but they won't say that necessarily. They'll just say Palestine should be free from the river to the sea, but that really means from the Jordan River to the Mediterranean, there should be no Jews in Israel. It shouldn't be a Jewish state. And nobody, can look at the map of Israel and say these Jews are going to, be put into, boats and moved back, moved around. Many of them are born in Israel and have, generations, families that go back hundreds or thousands of years. It's a disturbing time to be on a campus of so-called academic, credibility, where people are saying, I don't think you have a right to set foot here, that you should be boycotted based on your nationality. It's just, no, they don't do it for any other nationality. I'm not even talking about Pakistan. I mean, Pakistan has, been legitimized, and even though there were 10 times as many refugees and murdered people in the War of 1948, and I think there's still great tension there, and countries were made up from nothing. It wasn't like Israel. There's historical records going back 4,000 years that Jews have been there, and the Jewish people originated from there, and nobody really disagrees with that. But to say I don't have a right to set foot on campus, if I said that about Indians, Pakistanis, Chinese, Uyghurs, whatever, I would be barred from campus. These people get safe spaces in many cases, and they get to have have speakers come to campus paid for by taxpayers in the state of California. It's quite shocking to me, and it's become almost like a litmus test of your character. One side wants to ban speakers and the other side wants to have dialogue. And I just don't think it's possible to have peace in this point. I was optimistic on September 7th. I met many Palestinians, including Arabs. 20% of Israeli citizens are Arabs. They have political parties. They vote in their Congress. Essentially, there are all sorts of freedoms in the West that the West enjoys that no place in the Middle East enjoys. Freedom of speech, freedom of the press, freedom of worship. There's entire Muslim parties. So. And actually, the most happy, self-reported, satisfied Arabs in the world live in Israel, not in Egypt, say. So it's been very distressing that my colleagues in the West, who never set foot there, have this rosy image of what it could be like if only Netanyahu wasn't president. I mean, they push it on him like he's a version of Trump. They just hate the politics so much they blame him for everything. And some of them are my family members. So it's been very distressing for me, to be honest with you, Abhijit, since we spoke last, to see a pillar of scholarship, intellectual idealism, to have it disintegrate into kind of medieval thoughts about book banning and humans are implicit, and that we shouldn't allow them complicit, and they shouldn't be allowed on campus. It's been distressing, to be honest with you.
But what do you think explains these double standards? I mean, you cannot call for certain things, but you can do the same thing for Israel and call for the extermination of Israel. Why do you have these double standards, and what explains this?
I think it's explained by anti-Semitism. If I hated Italians, if I really hated them, it wouldn't be acceptable for me to say we shouldn't allow Italians into America. They shouldn't exist. We should exterminate them, or they shouldn't be allowed to exist. But I could say the state of Italy is illegitimate. Look, Italy is not 1,000-year old. Italy was formed in 1847 or something like that. It's not that old. I mean, there are states in America that are older than Italy. So to say America itself is a lot older. So the point being, you can't say that a people is legitimate if their one point of origin is illegitimate and shouldn't exist. It's eliminationist. It's suggesting that there is no right for one. There's one country on Earth that is the Jewish homeland. It happens to be the oldest country on Earth, besides India and China, and so maybe they tie for it. But the point being, it's one of the oldest. It's well documented. I mean, historical records, linguistic records, political dynasty records, currencies, all these things, archaeological, tens of thousands of years, people were living there. And then the origin of the Jewish culture began there. And it's the foundation of three of the world's major religions, right? So nobody disagrees that it existed for a long time. But nowadays, they go back and they say, well, it was formed illegitimately and it caused all these people. And really, the Jews belong in Poland. And, because of World War II, why do they get this place in Israel? Well, again, Jews have been there. There were no Palestinians. There's no such thing as a Palestinian mentioned. If you search on Google, search terms, you won't find the word Palestinian except for referring to a Jewish state. The word Palestine was coined by the Romans as an insult reminiscent of the word Philistine. So if you call someone a Philistine, it was an insult. In fact, there's no letter P in the Arabic language. There's an F, and Hebrew has the same
Indeed.
symbol, P and F. Yeah. So there was no currency. There was no president, prime minister. There was no culture. This guy, Yasser Arafat, who is Egyptian, born in Egypt, popularized this movement. And he was, of course, celebrated. And he won the Nobel Prize in 1993, the Peace Prize. And then later called for these intifadas. Intifada is a violent, bloody revolution against Israelis and Jews. And it's called globalize the intifada. So what is a Jew in America at Columbia University? Has never been to Israel, whatever. Maybe she is European in origin. Why should she, because she believes that Israel has a right to exist, just like I believe India has a right to exist, why should she be penalized and vilified? I think it comes down to the only thing she has in common with somebody in Tel Aviv is that they're both Jewish. And so if you didn't like Jews, it's a perfect time to express it safely by saying you don't have a right to exist and it's just called Zionism, when you know that 90% of all Jews are Zionistic. And so it gives you political cover in a sense. And I find it abhorrent. I find it, kind of extremely troubling that it's taken over college campuses and the most prestigious college campuses, MIT, Harvard, Columbia, Yale, and all the way down the line. And UCSD too has some element of it. When you have a small population that believes it, and again, I'm all for free speech. They should do it. But for them to say, I couldn't imagine saying no Palestinians should come here because the Palestinian people are educated by what's called UNRWA, which is this United Nations organization. So every member that committed a murder or rape on October 7th was educated in a United Nations school and the Palestinian Authority. So I would never, ever say that. I met many Palestinians in September. And again, I thought this is great. I thought, wow, for the first time, the people hate Netanyahu. They want him, kicked out. So he's temporary. He can only be in power for a little bit longer. He's going to get evicted. And then October 7th happened. And I thought afterwards, why did I not see this? Why did I? And I realized I didn't meet a single person from Gaza. Israel left Gaza completely in 2005. There hasn't been a Jew there. They actually excavated the burial sites of a couple thousand Jewish people who had died in cemeteries. Jews had been in Gaza, what's called Gaza now. They had been there since the 6th century. There's synagogues, temples, burial grounds there. Israel dug the graves up and transported them to the state of Israel proper. And they left businesses, greenhouses, farms, all destroyed. Gaza has been under Hamas rule since 2005. They took something like $9 billion in United Nations aid and intergovernmental aid, and they used it to build a 500-kilometer long tunnel system that went into Israel, into Egypt, north, south, east, and west with landlines, not even cell phones, because they knew they would be tapped by the IDF. So they actually used landlines. That's how they got away with it, coordinated it rather. And that I pointed out they could have built 20 Large Hadron Colliders. That's the length of 20 Large Hadron Colliders, and they chose to use this. And now they're suffering horribly. I agree, it's a humanitarian crisis. But just like every death in Japan, I don't put that on Americans for using the atomic bomb. I think it was horrific, but that was not America's fault. America didn't invade Japan. You can say anything about economics and so forth. And my favorite phrase is that, the Golda Meir said in the 1970s, the same thing keeps happening, where they attack Israel on holidays. It was a holiday in Israel when it was attacked. It was a Sabbath, a Saturday, a major holiday. And Golda Meir said when the Arabs, when the Palestinians love their children more than they hate our children, we can have peace. And you see the children are suffering. I think it's horrific. I spoke to Mo Gadat, who's an Egyptian by birth. He was at Google. He has a wonderful podcast and wrote about happiness. And we both agreed we have to stop children from suffering. It's horrific. But you have this ideology that is so durable that now it appears in America, 6,700 miles away. That Israel should not exist. I mean, how do you negotiate? How do you want to have a productive conversation when I don't think you have a right, your country, where you live, you're a patriotic person, you don't have a right to exist?
Yeah, it's terrible. I mean, Israel has been under siege since the time it was created, essentially.
Yes.
But you'll be surprised to know that one of the most unlikely allies Israel will have is India. I mean, Indians really admire Israel. Yeah.
Absolutely. And actually, one of the beneficiaries of this is going. So another thing that's just tragic, Abhijit. So the Jews come in all political persuasions, right? So some are extremely left. Some don't believe themselves that Israel should exist. Okay, they're fringe, but some are very openly pro-Palestinian. And in fact, those people live on essentially communist, kibbutzim. It's not a bad word. It just means a collective farm where they grow their own food and they clean this and that. But they live right adjacent to Gaza. Those were the towns attacked on the 7th of October. And the part of the reason that they were attacked so efficiently, and that the attackers, everyone in Israel is required to have a bomb shelter, but that wasn't supposed to be a bomb shelter from someone attacking you inside your own home. A lot of them were killed by setting fire to their safe houses in these kibbutzim. The reason that the Hamas and the Gaza civilians that participate, a large number of them were civilians, which is very scary and very sad, that they knew where to find the safe rooms to attack the Jews that were seeking shelter, was because they had employed members of civilians from Gaza to clean their houses. Here in San Diego, we're on the border of Mexico. So we have a lot of people that are legally here. They have work permits to operate in San Diego in America, and they cross the border every day. And it's totally legal. They had the same thing in Israel. Now they'll never do it again, ever. And so Gaza unemployment is going to be 99%, because their biggest trade partner and support is Israel. Israel provides them with water, electricity, telecommunications. I'm sure that they don't enjoy living under so-called occupation, but they could have taken the time and the ability to build bridges and bring together people to build the society, rather than just teaching their children this poisonous ideology, anti-Semitic ideology. And they could have been like Singapore. Tel Aviv is 20 miles to the north of Gaza, the northern part of Gaza. It's one of the biggest tourist spots in the world. It actually has the biggest, gay pride festival, if you're into that. I mean, it's a very open and it's I think it's the highest real estate per square meter in the world. Gaza is identical. It has the same terrain, the same quality of food, people. They could have had a mini Tel Aviv, but they chose not to. And I think it's terrible for them. I think, and so India is now supplying the workers that were displaced or not needed or not hired anymore from Gaza. So I think, yes, it'll benefit India. I mean, it's a small amount compared to your population, but the fact is they have this indelible tie, because I think Israelis rather, and Indians share this kind of common acknowledgement that that they have a legitimate structure, a Western structure. We don't have authoritarianism. We don't have dictatorships. We don't believe in mob rule. We believe in freedom of speech. India is the biggest democracy in the world. And yeah, it's not perfect. America's not perfect either. But to see the alternatives, Pakistan, I mean, how many people would willingly move to Pakistan, to Islamabad, from Mumbai? I think it's pretty small. And it doesn't mean that they're bad people. It just means they've established a civilization, a governance structure, and so forth that's exponentially ahead of many other cultures and civilizations on Earth. And I think India should be congratulated for that.
I think people should understand that Israel did try to implement the two-state solution from 2005 onwards. It has not worked. These guys, they elected Hamas as their government, and then we see what's happened. Well, I don't know what the solution could be. I hope there's a solution. I hope there's lasting peace eventually, but right now things don't look very good, unfortunately.
No, it doesn't. It's very depressing, and I'm sorry to end on a bad note. But the thing
Yeah,
that
no
gives me
problem.
hope,
Yeah.
the thing that gives me hope is that the spirit of the Jewish people is still alive. And you know what, Abhijit? I haven't gotten, there's an old saying like, in the end, when you are under attack, when things are bad for you, you don't remember the necessarily the negative things that were said about you by your enemies. You remember the silence of your friends. And I want to thank, India for standing so strongly with Israel and with America. I think, if I have a criticism of Biden, it's that he hasn't reached out and realized the significance that India plays now. And he's more worried about China and making deals with Iran and all these other ridiculous things that he wants to do. But hopefully that can improve. But you remember the people that have reached out the most to me, Abhijit, are two groups of people: Indians and not American Indians, but Iran. Oh, I don't. It gave me these balloons in the back. That was kind of cool. Let me go like that. See if that happens. I got this apple. There it goes again. All right. Yeah. Happy birthday. But there are two things. Two people: Indians. And Indians from India are, not just Indian Americans. Obviously, they're great friends and huge allies. But and Iranians. Now, why would an Iranian? I'm talking Muslim Iranian practicing devout Muslims reached out to me.
That's
Brian, are
interesting.
you okay? I'm so sorry to see this. I mean, I know you must be suffering. Colleagues, friends, Iranian practicing Muslims, because they know what it's like to live under an Islamic, the Islamic Republic of Iran. Is the full name of that country. They know not that Islam is bad. They practice Islam, but they realize that there's an ideology embedded within it that is counterproductive to technology, to human thriving, and to, quite frankly, scientific progress. And I think that I've been buoyed by that because a lot of my colleagues, Christian colleagues, American colleagues, they've been silent. Not all of them, but a lot of them. And so you remember that, but you really pay a great deal of gratitude to the friends that have reached out and said, "Just, are you okay?" That's all you have to do. Are you okay? How are you feeling? You don't have to solve it. You and I are not going to solve this problem, right, Abhijit? I mean, we don't know what the solution is. I don't think the solution is going to come for many years, and I don't blame Israel for that. But the bottom line is just to know that you care about it. That's a huge, huge confidence booster for me, and it really does, cause me to have a great deal of gratitude for the work that you do, and quite frankly, all the friends that I have around the world. So I want to thank you for that.
You're very welcome. Well, let's hope that things get better eventually. It's going to take time, as you said, but let's hope it gets better. So, Brian, thank you so much for another very interesting, enlightening conversation. I wish you all the best in the work that you're doing. I hope everything gets better. Thank you so much. Appreciate it.
It's always my pleasure. Thank you so much, Abhijit.
If you watched all the way to the end, I know you're going to love this interview with Rajendra Gupta, one of the pioneers of an alternative model that has a universe that's over 26 billion years old. And click here for a playlist of the best episodes from the past few weeks. See you next week on Into the Impossible.